Hello, everyone, and welcome to session number 60 of the Porous Media Design Talks. I am Chiara, and I'm joined here today in the studio by my friends Sara and Madi. We are part of the Interpol Young Academy and organizing members of the Porous Media Design Talks. And with this platform, we aim at giving the opportunity to early career researchers to present their work to the worldwide Porous Media community. Without further ado, I'm going to introduce our first speaker today, Sabrina Volponi. Sabrina's research is at the intersection between fluid mechanics and ecology. She recently obtained her PhD at the University of Notre Dame, the US, where she worked in the environmental fluid mechanics group. There, she studied transport processes through streams, fracture networks, and colloidal systems. She's currently a postdoc at the Washington State University, and she focuses on river and biofilm transport. Today, she will talk about how interception history drives colloid transport variance in porous media. Sabrina, the floor is yours.
Perfect. Hold on, let's get set up. All right, making sure everyone can see my screen. Thank you, Chiara, for that amazing introduction. So as Chiara said, I'm Sabrina Volponi. I'm a recent postdoc at Washington State University, where I'm working with transport through rivers, fracture networks, colloidal systems, and pre-asymptotic dispersion. Colloidal transport is going to be the focus of my talk today, specifically looking at how interception history drives colloid transport variance in porous media. Stick with me, and by the end of this talk, I promise you'll walk away with an understanding of the basics of colloidal transport, and you'll see a new framework for modeling and conceptualizing their transport. And with that, let's take it from the top. First, what is a colloid? Colloids are small suspended particles between 1 nanometer and 10 micrometers in size. They can be contaminants themselves, like viruses, bacteria, or environmental DNA, or they can be carriers of contaminants, like microplastics. Our understanding of colloidal transport has wide-ranging significance. For example, affecting our ability to maintain the health of groundwater aquifers, to even impacting the effectiveness of our industrial filters. But to understand their transport, it helps to try and conceptualize what's happening. So suppose we had an experimental column and we injected a concentration of colloids, and we were interested in their removal as they pass through a linear series of collectors, where a collector is nothing more than the porous media grain and its surrounding fluid envelope. So the colloids are going to approach the first collector in the system. Some of them are going to get close to the grain surface and attach, the rest will keep traveling onward. Same at the second collector. Some will attach, some will travel onward, same at the third, and so forth. It turns out the number of colloids that attach to each collector in the system is largely driven by the charge conditions of the colloid and the collector. When the two are oppositely charged, favorable conditions, a constant fraction of the colloid population will attach to each grain passed. What this means is if we were to plot the number of attached colloids versus distance on a log linear plot, we would observe an exponential removal of colloids with distance. Well, that's pretty nice and straightforward to work with. The problem is, in nature, we often observe like-charged colloids in collectors, or unfavorable conditions. While when conditions are favorable, we can assume that colloids that get close to the grain surface attach. The same is not true under unfavorable conditions, because repulsive electric double layer forces extending tens of nanometers from the grain surface can prevent colloidal attachment. So the question becomes, how can we model colloidal transport under unfavorable conditions? Well, people have tried to take the favorable exponential removal theory and apply it to unfavorable conditions by working in an additional parameter to account for that reduction in attachment, alpha, where alpha is the ratio of the number of attached colloids to the number of interceptions, with an interception being defined as an instance in which a colloid gets within 200 nanometers of the grain surface, which is about as far as electroosmotic forces extend. Now, the problem with this approach is that it still predicts colloidal attachment that's exponential. However, real experiments conducted under unfavorable conditions observe these plots of attachment versus distance, or a retention profile, that has this type of shape, multi-exponential, or this type of shape, which we call non-monotonic. These non-exponential retention profile shapes have been observed for identical colloids, both biological and non-biological, across a range of porous media environments, suggesting that their emergence is being driven by an underlying fundamental process. We try to investigate why these non-exponential profiles arise here. And to do this, we look at how grain interception history might be used to predict this non-exponential transport. Here's how we're going to do it. We're going to run a two-dimensional colloid trajectory simulation following the procedure of Alsgul et al. 2024. We're going to start with a porous media domain with grains arranged to form a periodic pattern. We're then going to solve for the velocity field in open foam, selecting conditions to mirror those experimentally observed in quartz sand. With the velocity profile in hand, we're then going to apply the one-piece Lagrangian particle tracking code. To do this, we're going to inject 200,000 colloids uniformly across our domain inlet. We're then going to solve for colloid trajectories by applying a force balance, considering the following listed forces. Now, let's zoom in a little bit. Even more, let's look at that grain and that single colloidal trajectory. Now, the blue line here represents the 200 nanometer interception boundary. Under unfavorable conditions, colloids that get close to this boundary will slowly translate along it until either attaching or getting kicked back into the bulk fluid. Notice here, the colloid attaches. To locally overcome repulsive forces, we incorporate nanoscale attractive regions on the grain surface called heterodomains. Now, we're not the first to use this heterodomain approach, and at the moment, it's the standing hypothesis for how to represent nanoscale heterogeneity on the grain surface. I'm happy to take questions on it at the end. But the important thing to note is that by changing the percent coverage by heterodomains, or these attractive regions on the grain surface, we can simulate favorability scenarios ranging from purely favorable with 100% heterodomain coverage to extremely unfavorable with 0.15% coverage. Now, as we monitor colloid trajectories through the system, we track the number of times a colloid intercepts a collector prior to attaching, so it gets within 200 nanometers of the grain surface, and the time between these interceptions. In the porous media domain shown here, I show 4 colloid trajectories, each undergoing a different number of interceptions prior to attaching. The blue line shows a colloid that intercepts a collector once before attaching, with that interception occurring here. The green line shows a trajectory where the colloid intercepts twice before attaching, happening here and here with the subsequent attachment, and so on. Okay, that's everything we did. Now let's look at the results. So in the plot before us here, we've got the number of colloids on the y-axis and the bulk fluid residence time, or the time spent outside of interception events, on the x-axis. I'm going to start by showing you data from our moderately unfavorable simulation. Here we go. Let's look at the residence time distribution for colloids that attach to the first collector intercepted. Notice this forms a straight line on a log linear axis, indicating exponential removal. So let's fit an exponential through this with a decay rate k. Now let's consider the residence time distribution for colloids that intercept 2 collectors prior to attaching. Well, we know removal at the first interception is given by an exponential distribution with decay rate k. Assuming the same physical processes govern removal at each interception, then removal between interception 1 and 2 should be given by the same exponential with the same decay rate. And the total residence time distribution after 2 interceptions, the green points on the plot, should look like we sampled the same exponential distribution twice and added together the draws. And for 3 interceptions, it should look like we sampled the same distribution 3 times, and for 4 interceptions, 4 times, and so on. Mathematically, we can describe the summation of distributions through an operation known as a convolution. And conveniently, the convolution of n exponential distributions with the same decay rate can be more concisely described by a gamma distribution, which takes 2 parameters, n, the number of interceptions, and k, the exponential removal rate for those single interception attachers. So let's see how well our gamma distribution, parameterized by n and 1 over k, performs. Here we go. Now the points, remember, represent residence time distributions from our simulated data. The lines represent the gamma distribution. The gamma distribution is solely parameterized using information from the single interception attachers. The agreement between subsequent points and lines, the green, yellow, and red, suggests that the gamma distribution, using just information from the first interception, can predict the subsequent residence time distributions. And we can do this for a range of favorability scenarios, looking at purely favorable, then slightly unfavorable, moderately unfavorable, and then extremely unfavorable. What this demonstrates is that removal processes are in fact repeated at each interception, and present and future colloid grain interactions arise naturally as a consequence of their past trajectories. Pretty cool. Okay, now let's take a breather for a second. Quick recap. We started at the beginning of this talk by showing that in traditional colloid filtration theory, it's assumed that a constant fraction of colloids are removed for each grain passed. But this fails to accurately describe colloidal removal under unfavorable conditions. What we just saw with the gamma distributions is that we see a repeated process of removal between interceptions. So let's pivot our focus and consider removal from an interception-based perspective. Here's how we're going to do it. Suppose I injected N0 colloids into an experimental column. In order for them to attach, they'll eventually have to undergo a first interception. At the first interception, we're going to say a constant fraction of colloids are removed, alpha, where alpha is that ratio of attachments to interceptions from the traditional colloid filtration theory. The remaining 1 minus alpha fraction of colloids survive the first interception and will eventually have to undergo a second in order to attach. Again, at the second interception, an alpha fraction of colloids will attach, and the remaining 1 minus alpha fraction will continue on to a third interception, and so on. Generalizing this process, we can describe the number of colloids that attach after n interceptions relative to the number injected analytically, in an expression that depends solely on alpha and the number of interceptions. Let's see how well this predicts our simulated data. Now, we can get alpha from our simulations by looking at attachment at the first interception. With that, we're ready to use our analytical formula, and we can look at the fraction of attached colloids on the y-axis with interceptions on the x. We're then going to compare how well our analytical formula, which will be represented by stars, matches our simulated data, given by the circles. And we're going to do this for the different favorability scenarios explored, with favorable being represented by 100% heterodomain coverage and extremely unfavorable being represented by 0.15%. Here we go. What I want you to notice is the close agreement here in general between the circles and the stars, suggesting that our analytical formula is doing a good job of capturing the simulated attachment across each interception event. We can do the same thing for survival, this time comparing the fraction of unattached colloids with each interception event. Again, notice the agreement between circles and stars. What this means is that we can predict removal and survival under unfavorable conditions when we think about transport as a series of interceptions rather than as a series of grains. And the removal and survival that we see is exponential, which is what the traditional colloid filtration theory was trying to achieve. Great. Now, let's think about how we can relate these interception events back into physical space, which we're primarily interested in. Okay, these are the same 4 colloid trajectories that I showed you earlier, but this time the trajectories are colorized by the number of interceptions that occurred at a point along the path. What I want you to take away from this plot is that increasing the number of interception events does not necessarily correspond to an increase in linear travel distance. Notice the colloid in this trajectory here undergoes 4 interceptions, but doesn't travel as far as the colloid in this trajectory that only undergoes 3 interceptions. So while attachment decreases by a constant fraction with successive interceptions, the same is not true for physical space or for successive grains. Moreover, it suggests that the emergence of non-exponential retention profiles in physical space comes from the overlap or superposition of colloids with different interception histories. For that last point, let me draw it more clearly through a thought experiment. So here we're taking the residence time distributions from the moderately unfavorable simulation, and we're scaling the colloid populations so that the fraction of colloids that attach at the first interception composes 99%, 80%, and 10% respectively. We're then going to look at the residence time distributions for colloids that attach at the first 8 interceptions, and we're going to trace out the maximum removal observed in yellow. Here we go. For the 99% fraction, we see this exponential shape fallout. When the single interception attachers compose 80%, we see a multi-exponential, and for 10%, we see a non-monotonic shape. We then compare these distributions to the corresponding retention profiles, or plots of attachment versus distance. And what we're going to see is that we observe the same shapes for the retention profiles, being exponential, and then multi-exponential, and then non-monotonic. What this means, so first, these non-exponential retention profile shapes are coming from this overlap or the cumulative stacking of these residence time distributions for colloids with different interception histories. And the transition from exponential to multi-exponential to non-monotonic shapes are driven by the fraction of fast attaching or single interception attaching colloids, because these are the ones that are driving the significance of that initial exponential signature. Okay, and with that, let's tie this whole thing up. So the first thing that we saw was that the self-convolution of travel time distributions for single interception attachers produced the observed travel time distributions for multiple interception attachers, indicating that interceptions are governed by equivalent or repeated processes. We then saw that if we collapse space and time into interceptions, we could devise a framework in which transport under net repulsive or unfavorable conditions could be predicted using a constant attachment efficiency, or alpha. And finally, we saw non-exponential attachment profiles were likely the result from the overlap of colloids with different interception histories in physical space. I appreciate the opportunity to speak with you all. My email is at the top of the conclusion slide, and I'm happy to take any questions. Thank you.
Thank you very much, Sabrina. Very beautiful talk, very interesting. Maybe I take the first question, and meanwhile, audience can type down their questions, and also people in the studio, if they have questions, they're welcome to ask it. So actually, at the end, you answered one of my questions. I'm going to go ahead and ask about, do you think the geometry of the porous media that you have is going to have is going to play a role in like how much particles you're going to, how much of your particles going to get stuck in the porous media? Or another way of this question would be, how do you like, because you were working at a very small scale, like how do you define that heterodomains, and how much of the particle is going to attach to the surface for a larger scale, like another applications?
Okay, let me make sure I've got your question right. You're interested in how the geometry of the system and heterodomain coverage impacts the results that we saw. Did I get that right?
Yeah.
Brilliant. Okay. It's a really fair question. The biggest limitation of this study here is that everything we're doing is in 2 dimensions. And so we're dealing with circles as opposed to spheres. And so when we're dealing with low heterodomain coverages, these nanoscale attractive regions, once we're putting them right now on the perimeter of circles. And so that limits how much things can vary between, for example, our different favorability scenarios. Our goal is to eventually up this to a 3-dimensional setting where we think we'll see stronger contrasts between those different heterodomain coverages. So first, going from 2D to 3D is going to be a big step. We suspect the same patterns will fall out just because of the underlying processes won't change, but it's definitely something that needs to be explored. In terms of actual geometry itself, there have been theories that different arrangements and packings can impact attachment and retention. Like there's an idea of straining, where if the pore spaces between the grains are too small, colloids will get trapped because they can't actually fit through those narrow pore throats. But studies have shown in porous media domains where those pore throats are large enough that straining shouldn't be an issue, these same types of non-exponential retention profiles arise. So I think if I were to speculate, because we've really only played around with this one geometry here, I would speculate shifting things around likely won't change much in 2 dimensions, but 3 dimensions is something totally new to play with.
Yeah. Okay. Thank you very much. I might ask another question. Is there any way to experimentally measure these heterodomains, like the percentage that you were giving in your simulation? Is there any experimental way to actually measure them in a real system?
That one is a beast on its own. It's actually very hard to experimentally measure these heterodomain coverages, but a lot of people have been out there trying with different analytical and chemical techniques. But it's a lot of speculation on what exactly is driving this nanoscale heterogeneity. But people are finding that you need to include it in order to overcome those local repulsive forces.
All right. Thank you very much. Yeah, I think we have a question in the comment section. I don't know how to pronounce that name. Mauricio, I think, and I hope that I'm pronouncing it correctly. I was wondering if there is a way to relate the number of the interactions with the distance, time traveled before attaching.
Ooh, okay. So what we've found, the number of interactions. Okay, so I'm going to start with the time one because that's already in the plot that I've shown here. Let me go back to it for a second. Let's look over here for a second. Okay, so a colloid traveling through our system is going to spend time. It's either going to be traveling through the bulk fluid, so far away from our collector, that grain surface. It's going to be in an interception, so within 200 nanometers of that grain surface, or it's going to have attached. What we see in the plot here is the number of colloids that attached after a specific What we've seen here is colloid residence time distributions for different interceptions. So how long did a colloid spend before attaching, given it attached the first collector it intercepted, the second collector intercepted, and so forth. What we found from playing is that the time spent within that interception, so within 200 nanometers of the grain surface, is ridiculously small compared to the amount of time spent traveling through the bulk fluid. So it would be a good estimate for the number of interceptions at a given time if you were to say at 1,000 seconds. Ooh, hold on, the mouse here does not quite match where I'm looking. At 1,000 seconds, let's just trace this line up and count the number of colloids that we hit. And I think that would be a good estimation of at 1,000 seconds, how many interception events have we seen? For distance, we're finding we can go back and forth between residence time distributions and physical space by dividing by the velocity. I skipped this plot in the presentation for the sake of time, but is this the right one? Yeah, what we find is we can divide by velocity, and that matches what profiles look like if we were to look at attachment over a distance. If we took our bulk fluid residence time distributions divided by velocity, that's what our retention profiles would also look like within our system. And our gamma distributions still do a good job of fitting this. And the same way, start at a distance, work your way up and add. Does that make any sense? Or at least does that get at the question?
Yeah. Okay, thank you very much. I don't see any more questions. People in the studio, do you have any questions? Okay, all right. Thank you again for the beautiful talk and very interesting topic. We'll move to the next speaker now. Our next speaker today is Mohammad Hossein Khosravi. He is currently a PhD student in earth science at the University of Toronto with a background and interest in the seismology, rock physics, rock mechanics, and data science. He did his master's and bachelor's degree in the petroleum exploration engineering at the University of Tehran and Petroleum University of Technology. And he is currently conducting research on the application of deep learning methods to microseismic signal monitoring. The floor is yours, Mohammed.
Thank you. Thanks for your introduction and having me here. Hello to everyone. As you mentioned, I'm currently a PhD student at the University of Toronto, and what I'm doing now is not directly related to the Porous space. It is induced seismic signals processing using deep learning methods. So when I was invited to have a presentation for this talk, I decided to present something from my master's degree, which is titled Quantitative Characterization of Carbonate Pore Systems using Seismic and Well data. So a fact about today's presentation is that since the paper of this presentation, this research has not been published yet, I cannot show the figures or all the results, but I try to tell all the details and what we did in this research as much as I can. So the content of this presentation can be divided into introduction, methods, and conclusion and future works. So I go through each of these sections and try to explain them as much as I can. So in the introduction section, I should make sure that you all know all the basics. So at first, I want to have a short definition of rock physics. As you know, in all reservoir studies, we have two main properties. That the first one is reservoir properties that we can say, for example, porosity, saturation, or permeability, and another class of properties that we work with in reservoir studies is acoustic properties, for example, VP, VS, or all the elastic modulus that we have in acoustic properties. So there always have been a challenge to connect these and relate these two types of properties that we have in reservoir studies in the physical way, not with estimation. So a tool that helps us to connect these two kind of properties together is called rock physics. Yeah, rock physics is a tool that helps us to for example, when we do forward modeling, we can have reservoir properties as inputs and calculate acoustic properties in the outputs, and the inverse rock physics modeling is vice versa. So each rock physics modeling has some parameters, and we need some parameters to in order to do the modeling. So in carbonate reservoirs, there are some rock physics model parameters that are a bit challenging to be calculated because of the complex pore geometry and geology of carbonate rocks. So let's go through the model parameters that we need for rock physics modelings of carbonate rocks. So rock physics modeling of carbonate rocks generally needs four main type of inputs. The first input is called mineral properties, that we have them from the reference books and the measurements that we have. So we can say that it is available. This input data is available. Another input data for carbonate rock physics modeling is fluid properties, that we also have this from well test or laboratory measurements. So it is not a problem too. And the third input data for rock physics modeling of carbonate rocks is porosity value, that we also have them from well log data or from laboratory measurements. And the fourth and last input data or parameter of rock physics modeling of carbonate rocks is pore geometry. That it's a bit challenging to be calculated, and actually we need to indirect. We cannot have them directly. We should do some apply some algorithms to calculate them for rock physics modeling purpose. So, what is pore geometry? I can say that in geophysics we uh, know pore geometry as another representation of pore types. What do I mean with this? Let's talk about this in the next slide. As you know, we have different pore type classifications. We have petrophysical pore types classification or geophysical pore type classifications. In petrophysical pore type classifications, we have, for example, these kind of pore types: cracks, interparticle, intercrystalline, moldic, vaggy. And what is important in petrophysical or geological pore type classification is how the pores have had been created, and what was the reason of their creation. But in geophysics, generally, we have these three main pore types that are named cracks or soft pores, reference pores, and stiff pores. And how do we classify these pores is based on their geometry. So let's say in 2D we have these. We should, since we want to model these pores, we say that they are in a form of ellipsoid, and we define uh, alpha, which is a over b, as a parameter to divide pores to these three main types. So why we look at the geometry? Because we what is important for us is how these pores are influencing the seismic velocities and seismic response, and their geometry has the most impact on the seismic properties that we have. So it doesn't matter how the pores are created. What is important is what is their geometry. So having this parameter, we can say that stiff pores are those parameters, are those pores that have alpha close to 1. Cracks are those porous spaces that have alpha close to 0, and reference pores are something between that are ellipsoid, have ellipsoidal form, or uh, actually figure, let's say. So in a real actually world, we, for example, we can have this thin section image that we can say that these pores that are here are kinds of cracks that has alpha near to 0. These pores are kind of reference pores that are alpha around 2 or 0.2 or 0.3, and these pores are stiff pores that have alpha close to 1. So this is finally we can divide the porous space of rock to these three actually categories. So what is the objective of research is to predict the geophysical pore volumes, which are these, in 3 dimensions for the whole reservoir. So how do we want to do this? Let's talk about it in the methods sections. So the how do we want to determine geophysical pore types quantitatively? Uh, it is a workflow that proposed by Kumar and Han in 2005 for prediction of geophysical pore types. Uh, as you can see, there are VP and porosity total as inputs, and finally the volume of different pore types are given in the output. So I don't want to go through the details of this algorithm. What I want you to take out of this algorithm is that it takes VP and porosity total as inputs and do some processing, and finally gives us the volume of different pore types. So another algorithm that is a modification to the previous algorithm was proposed by Mir Kamali et al. In 2020. And in this algorithm, they used VS data uh, um, in addition to the VP and porosity total, which is so helpful to have a more accurate actually image of pore types underground. So finally, they also in this algorithm they predicts a volume of crack, reference, and stiff in the output. So using this algorithm, we determine the pore types at the well locations. How we had these three well log data of VP, VS, and porosity well log data in all at all well locations. Let's say like this. So after applying the Mir-Kamali et al. Algorithm at the well location using these three well logs data as inputs, we had pore volume fractions, which is in each depth, how much of our pore space is occupied with each of these pore types. So we applied this algorithm to all the wells that we had and more wells that are not shown here. So finally, we had the pore the volume fractions at all the wells, and then we need to validate this data. We used thin section image to validate the results that we had. So we went through all of this data and thin section image that we had, and the next image data that we used for validation was SCM image. We also used SCM image to validate the data that we had, and we predicted. And the third the image data that we used for validation purpose was image logs, and we also used image logs to validate the results too. And finally, our validation results showed that our predictions of pore volume fractions was generally verified by all of these image data. So which shows that our these are quite accurate to be distributed in 3 dimension in the rest of the workflow. So we use these validated results for each well like this. We had all volume of each pore types as a well log. So on the other hand, we had seismic data too. That this seismic data is in 3 dimension. So we applied pre-stack seismic inversion to calculate VP, VS, and density in 3 dimension for the whole reservoir. And we also had seismic attributes that directly calculates from seismic data. So what we did, we used these seismic data, so these actually features that generated from seismic data as features of ML model, and these data that are that we calculated as a target of ML model. We decided to use this seismic data at the well locations to predict these targets that we had here at the well locations too. So we trained and tested the model at the well locations, and after getting the good result, we had these data in 3 dimension, but we didn't have these data, well data in 3 dimension. So we applied the model that we had and trained and tested at the well locations to the 3 dimension to finally have these volumes in 3 dimensions. So finally, we had these cubes of each volume of pores. And what is the implication of this prediction and this calculation? The first one is that we can have dominant geogenetic processes at each region and each zone of the reservoir to see what was the major and dominant geogenetic feature at that place. So, for example, when we have high volume of stiff pores, it can be a representation of dissolution occurrence, or when we have high volume of cracks, it can be a representation of fracturing occurrence. In the other hand, we also can have a permeability estimation using these results. For example, a high volume of cracks can be a representation of high permeability, and a high volume of reference pores, since the reference pores are generally interconnected, it can be a representation of high permeability. And high volume of stiff pores, since they are generally isolated pore, can be a representation of low permeability. So we did this analysis, and our results were confirmed very good with the geological interpretation, with geological data, and so I can say that this kind of analysis at the using seismic data and well-like data can be so helpful to have a good view of the reservoir, and for can be used for the future development of the reservoir. So about the conclusion and future works, I can say that our research showed that this method is a practical and straightforward way to quantitatively compute the volume of various pores in 3 dimensions, and 3 dimension pore volumes allow for an overall view of the presence of diagenetic processes and permeability state, which is useful in future reservoir design. And AI models can be used in determining the complex relationship between seismic data and pore volumes. We showed this at this research. So, and about the future work, I can say that the AI model that we employed in this study was a simple neural network, and employing more advanced neural network like CNN or RNN can be helpful to have more accurate and better outcomes. I want to say thanks for your attention, and I'm happy to answer to your questions.
Yeah, thank you, Mohammad, for the very interesting talk. So again, for the audience, feel free to ask questions in the comments. We'll start with a question from myself and then from the studio there. When you apply like when you're using seismic data, basically you have like sparse data and noisy data, right? So my question would be, how would your theoretical pore volume prediction sensitive to the uncertainty on your data, your input data, like the porosity, p wave fraction, p wave velocity, etc.?
Thanks for your questions. I just want to make sure that I understood your questions correctly. Well, you want to know did we actually observe the uncertainty of seismic data in our results? So yeah, these seismic data, when we are doing seismic inversion, the data is tied. We do a well to seismic tie analysis. With that, we try to correlate the results with at the well locations to have a seismic data that is coordinated with the well data too. So this is the way that we make sure that our seismic data has is associated with the well-like data, and finally we applied that to the 3 dimension. Yeah, it is the only thing that we can make sure the seismic data is accurate.
Yeah, all right. But then how your prediction is sensitive to your input parameters, because when you measure like p wave data and like total porosity from the beginning, how do they affect like the sensitivity on the geological pore volume, for instance? If your input parameters are uncertain, which
when in our input parameters were VP and velocity at the well location, VP and the velocity at the well location, at the same time VS, and we say in seismic domain we consider the well-like data as very accurate results, and
okay.
yeah, it is.
Yeah.
We calculate them as very accurate.
Yeah, because it would be interesting to see the sensitivity to this kind of parameters on the prediction of your geological features.
Mm-hmm. We haven't had any sensitivity analysis, but I can say that what I can say is that well-like data for us is the more accurate data that we have in seismic.
Okay. All right. And then about your prospects of applying CNN to like perform the inverse modeling and recover like your geological features. This is well known that this requires lots of data. So are you planning to use only experimental well-log data or using the simulating based also data?
It was a part of my master's degree, and as you said, yeah, the data that we have for training and testing this approach is just well-like data, and we always we don't have so much well-like data to train our model. So I'm not sure CNN or other more advanced deep learning model can help, but I haven't tried yet to see can they have any improvement to our simple neural network or not.
Okay.
Yeah.
Yeah, thank you. Because the thing is, if you combine experimental data with modeling data, then you have to make sure that you properly like balance the uncertainty on both.
Yeah.
Cool. Cool perspective for the future. Any question from the studio? No. So we don't have any question from the audience right now. So I think we can finish here then. Thank you again, Mohammad, for your interesting talk. So thanks again to both our speakers for sharing their research with us today. I just wanted to advertise our next session. Yeah, thank you. So our next session is set around the 17th of September, and it will feature Syed Farouchi from Imperial College of London and Tobias Forlund from Luleå University of Technology in Sweden. And it will be at 3:30 Central European Summer Time. So yeah, and this is us. And if you have any comments, feedbacks, and want to be involved as speakers, please feel free to contact us at our Gmail address. And thanks you once again for joining the session today, and stay tuned for the next Porous Media Dictum. Bye everyone.